Yeah, we've got Edwin and Cole signed in, but people won't see, and that's fine. They're on break, so you can't see them, but I can see them. Okay. So to find the equation of any plane, we need two pieces of information. What do we need to know?
The point in the normal vector.
Are we told either of those?
We have the point.
The point we have, which is not uncommon.
Normal vector is just a gradient.
Exactly, the normal vector is going to be gradient. So now we need the gradient of this function. So if we get that that capital F function by itself, which is kind of the weird part here since we're not really told the z on this one. We're going to have y over x minus z, not minus 1. I'm ahead of myself again. Okay, so imagine the whole thing's equal to z, subtract z from both sides so we can get that capital F function by itself. So the gradient of this then is going to become our normal vector. And what did you get for that, Brett?
I got negative y over x squared for x. Y, I got 1 over x. And for z, I got negative 1.
So our gradient, we should just be able to go back and plug our point in to know specifically at this point what is the gradient equal to. And this point is probably different than what you got, but the process should be the same there.
Which one?
Yours, okay, so yeah, we'll just keep with what's here. So what do we get? That is 4 over 1, so negative 4, 1 over 1, and negative 1. And then from there, it's just going back and plugging in and hopefully just working through the algebra there. It's possible if you've done this and it's marked as wrong, every now and then there are problems in the homework that the answers are wrong on. So if you've done all this and everything works out, I'll go back and check that. But from here, remember, this is going to be our A, our B, and our C. Our points up there, so we have negative 4 times x minus 1 plus 1 times y minus 4, and then minus times z minus 4. All equals 0.
This is also
right?
from the last, right?
Yes.
This is where I get screwed up. I'm like,
Okay.
yeah, this is trying to think of two separate ones.
So if we simplify that, we'll finish it off. Negative 4x plus y minus z equals negative 4.
Is that plus or is that should that be or is
So to distribute the negative there, so we should always be happy. You mean by the z part?
I thought it was a plane. It was positive, negative, positive.
No, they're all positive for a plane. It's plus plus plus.
What? Oh, I'm thinking.
When you're doing the cross product,
Cross product.
where it alternates. So
That's
that's
right.
where it is there. Get the little sign off. Yeah. So it's everything's plus 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 when you do this. Positive for x, minus z. And then yeah, point would be different, but you had all the right steps besides this last piece.
I was going to say because I was getting the same. I was doing the same steps for the other one. I got it wrong too, but that makes sense. Plus plus.
Yep. Joe plus and I fixed it. Okay. All right. Any others on the homework? The one that's due this Sunday is over. Just pull it up instead of trying to remember.
All those.
13.6, 7, and 13.8, which we're going to get to today. We'll start that today.
Wait, the one that's due this Sunday?
The one that's due this coming Sunday. So 13.6 we finished last time. 13.7 we finished almost all. We got a little bit left to do. And then we'll start at 13.8 today. Yep, that's 13.7. It is kind of a long assignment. There are a lot of problems on this one, but some of the problems should be pretty easy. Like just graph it, go back and look at the graph over there. Not all of them. Anything else to take a look at now? That should hopefully fix some of the rest problems. Okay. If you did get far enough in this homework to look at what's coming up here, so I'll just pull up one of the questions. Oh, that's one that we just did. Okay. What we're going to be talking about doing a lot in the next section, last section for this homework, is finding extrema, and it's very heavily related to what we've been doing. It's still going to go back and using the gradient and using a lot of ideas that we had from Calc 1. So that's what's coming up. We'll get to that in just a minute there. We left off on page 36, is the last one we finished.
What question does this number two? What page?
36 on these. It looks like question 16 is the old stuff still, and then 17 is for the new stuff.
And that's for this Sunday, right?
Correct.
Okay.
And the homework for the Sunday after that, I don't know if it's available yet, but the stuff should be popular. And I tried to go back and fix that weeks out. Yeah. So the rest of chapter 13 should be showing up at this point. Okay, talking about tangent planes. So that reviewed a little bit of what we were talking about, and actually the top of this page has the only formula we've gotten to so far. So let's just go right there. So top of page 36, that's what we're talking about. And this looks super complicated. There's a lot of stuff going on here. But if we break it down, it is pretty much just saying we're going to write the equation for a plane, and the normal vector we're going to use is the gradient vector. So that's why all of this stuff looks a bit more complicated. If we look at these coefficients, this guy here, this guy here, and this guy here are all just going to be a number. Whenever we have those little subscripts, we're plugging the actual value point. We're just going to have some value, some kind of A coefficient, and then our B and our C coefficient here. Looks definitely more complicated than it actually is. Work through a few of those problems, going back and find the equations for a plane, and then top of page 37 is where we are at now. This is another way we can kind of approach this stuff here, and this is not something necessary to go through and do. We'll kind of see why it works out here, but it's a different way we can go through and look at these problems. The first thing we had to do when we were working those problems before we can go through and find the gradient, make sure we had it all set equal to 0. And this kind of just avoids doing that step there. It's a fairly simple way to go through and fix it here. If we leave the equation as z equals f of x, which is pretty common to be given to it as kind of your standard form, your function notation, if you will.
Ms. Nicole?
Yes.
Could you please record this section for Brian and Murillo?
Yep, I've got it recorded, I think. I've got
All right.
dot there. Thank you for reminding me.
Yep.
So if we think about our function as z equals the function there, so 0, we can go back and rework the situation here. So let's go through and do that. If we have this just general notation there, we're still going to go back for this general formula to kind of see what happens and go through and subtract z from both sides. So we know that this all has to equal 0. And now we are in the same place that we had before. That says more clearly an x. So if we have some function solved for z, all in terms of x and y, that's what that f of x represents, and just doing it the way we did before, we get this. The next thing we need to go back and do, it says the previous theorem. The previous theorem is just the one for the tangent plane. We really just need the gradient vector here. So if we find the gradient vector of this function, which is now in terms of 3 variables again, the partial derivative with respect to x is going to be whatever the partial derivative of this function is with respect to x. We don't know the function, so just keep it general. The partial with respect to y is similarly just the partial derivative of that function with respect to y, of whatever that is, of this original function, just the function. Because when we're subtracting z, that z term we're basically guaranteeing doesn't have any x and doesn't have any y. It's just going to be minus z. Because if we have that explicit form, that should be the case there. But then the partial derivative with respect to z is going to equal what? Okay. Yeah, it's going to equal -1. So not quite 0, but right idea. Okay, it's going to equal -1 every single time. The only place z is going to show up if we have this original function solved for z in that very beginning. When we subtract both sides, we're guaranteed to have that circle part. We know the partial derivative is going to be -1 there, which means our equation for a plane, so the tangent plane, to get back to actually that previous theorem I mentioned, we are going to have the partial derivative with respect to x evaluated at that point, still times x minus x0. So that part's basically the same. We just drop off a little z component. Similar for y, we're going to add the partial with respect to y at that specific point, times y minus y0. But then since z's derivative is always going to be 1, we're just going to have minus z minus z0. So it doesn't really simplify things a whole lot. It's really doing the same exact process we did before. And if you don't want to have to pay attention to a new looking formula, then ignore this. You can do it the same we did before. But many times we are given equations in explicit form, okay, where we have z equals something in terms of x and y. And so this does make it a slightly bit more efficient method. And so is it necessary? No. You can do it the same way we just did. But if you have explicit form, then you can go back and use this, and it just saves a little bit of time there. Like you said, my equation is in the opposite order, so flip back for a minute here before we go through to the next one. If we were given example 2 then, and we went back and did this one, this would be a good case to go back and use it on. You have z equals everything in terms of x and y. We went through and found the partial derivative of z was -1, just like we did there. We could have gone back and used that new way to write this formula for this problem here. So I'm just going to note that off to the side. See page 37. Definitely not something we have to do. There was nothing difficult about doing it this way, but another way to look at it there. Okay. All right, so back to where we were, page 37. Example 3 is a little different than what we looked before. Find the equations of the normal line to the surface at the point. So we haven't really worked with normal lines up until this point there. What does a normal line mean? Perpendicular. So we're talking about the line that's perpendicular to the surface at this point here, which has a lot to do with the tangent plane. We're still going to go back and be finding the gradient here. If you remember back to some of the things we talked about last week, we reviewed planes and lines. When we're working with the plane in 3 dimensions, we need a point and a vector that's perpendicular to it, which is our gradient vector. When we're working with a line in 3 dimensions, we still need a point. We need a vector that's parallel to our line. So since we're talking about a line that's normal to the plane, we still get to use the gradient there. We don't have to go through and develop some new vector for this. So in order to write the equation for a line, we need to have a point, and we need to have a vector that's parallel to the line. And so in this case, that vector is still going to be the gradient. So we're going to look for the same information. We're just going to use it differently. Instead of going through and finishing write the equation for a plane, we're going to write the equation for a line instead. But very, very, very similar steps there. So we are given the point. The point is this guy right here. We need the gradient, so let's do like we did before. Let's go ahead and get this to be that capital F function. So get x, y, and z all on one side. Not a huge step in this one, since the derivative 12 is going to give us 0 anyway. It doesn't really hurt if we didn't do that, but it's a good habit to have. And then here we go. We need the gradient. So partial derivative of this function with respect to x is going to be yz. Partial with respect to y is going to be xz. And partial with respect to z is going to be xy. This is going to tell us the coefficients for our line, so let's evaluate it at that specific point we care about. -2 times -3 is +6. 2 times -3 is -6. And 2 times -2 is -4. So there is our vector that's parallel to our line. We have to go back and write the set of parametric equations using the point they gave us and this set of coefficients. So if you recall the structure, we're going to have the point, which is 2, plus the vector times t. And we keep that pattern going. So y equals -2 minus 6t, and z equals -3 minus 4t. And that is it. That is the set of equations for our line. So much like a lot of the problems, the math part isn't really difficult, but understanding what they want us to do is going to be the challenge. Making sure we recognize that we're at a normal line, we need to find the gradient because the gradient is perpendicular to the plane at a specific point there. Also with this, remember when we're doing lines, there are an infinite amount of ways we can go through and describe this. You're probably going to have to go to this point no matter what because it's the point that we're given here. However, if you for some reason really wanted to find a unit vector, you can go through and do that. If you wanted to scale this vector and divide everything by 2, you can go back and do that. As long as it is a parallel vector, it doesn't really matter what those coefficients are. Keep it simple and don't bother going through those extra steps, but there are a lot of different answers you can have for this one. This isn't the only answer. Those coefficients of 6, -6, and 4 can change for a lot of different things.
So this is the equation of the line that is perpendicular to that point.
To the surface at that point there.
At that point.
So
And the other problem we were doing is the equation of a plane at that surface.
yeah, so let's just go back and graph these last two. So in the example 2, our equation was this. Oops, that doesn't have a coefficient. That's one. Okay, so here was the equation we were working with in example 2. The point we were at. Thank you. So there's that little blue dot right there, and I'm going to go ahead and turn this so that our x and y axis positive points are facing us. And then the equation we got for a plane, I don't have mine written out there nicely.
The equation.
Uh-huh.
-2x. minus AY minus 10Z equals negative 15.
So there's the equation for the plane at that point there. So let's I want it to spin, it won't spin. It's just stuck on. There we go. So we can see at that specific point we're talking about just touching it at that little spot right there. So yes, exactly what you said. In the previous problem, we're saying, okay, well, if I just lay a sheet of paper so it just touches the surface, what's that sheet of paper going to look like there? And then what we're doing now is we're saying what you said. I'll go ahead and graph anyway. So x, y, z equals 12. Oh. Why did it not graph it? I shouldn't have to. Let's put multiplication symbols in there like that better. Nope. We'll try it. So z is equal 12 over xy. Okay. Yes, I guess it does that better. So there's a surface we're talking about in this question.
The point is 2, negative 2.
And there's that point down here on the bottom of this. Oh, there it is down there on B. And do I remember how to do a line? All right, what was our point for our line? 2, negative 2, 3, same point, right? And our direction vector.
Was negative 6, negative 6, negative 4.
What?
Not right.
Oh no, it is on the bottom there. Don't spin. Don't spin. Kind of hard to see. It's a bit more complicated here to look at this guy, but let's see if I can get that line up. So here is, no, let's go for the perpendicular. I think I may have typed something wrong. Is it positive 6 for the first one?
Yeah.
Yeah.
Oh, is it?
Yeah.
Oops.
Okay, that looks better. So there we go. Now we can see that at that point, that line kind of is perpendicular to what's going on there. So a lot of work for a fairly boring, complicated picture. But
So a normal line is, when asked for the normal line, it wants the parametric.
yes, when it asks for a normal line, it wants a set of parametric equations. We talked about parametric and symmetric equations. Don't worry about symmetric equations. We've been working on parametric. Let's just stick with that. So yes. Okay. Other questions before we go on? Next idea is a little different than that. Still kind of follows from what it built on it. Back in chapter 11, I believe, early on in the semester, we talked about finding the angle between two vectors here, and we had this formula. So let's just copy from chapter 11. We talked about dot product. We had this. We went through and used it a few times here. We're going to use it again. We talk about how we can find the line or of inclination of a plane. We are always going to be talking about the angle that a plane makes with the positive x-axis, the xy plane, I should say. Okay. So if you imagine that xy plane, and we have a plane, which you can imagine being like your tangent plane. If your tangent plane intersecting this thing here, we can go through and measure the angle between these two items there. Okay. So we're going to kind of take this idea of working with vectors, and we're going to apply it to be able to working with planes there. There's a picture on the next page that talks about this a little nicer. Note here, though, that we are always going to report this as an angle from 0 to pi over 2. And the way we're going to change our formula to make sure that happens is basically just stick absolute values up on the top here. That way we know we're just talking about it in that, within that range there. We're going to kick out the negative values for x. But on top, next page, here's a picture. Hopefully it makes more sense there. Maybe. There we go. All right. So that kind of tanish plane down here, this is the one that's in our xy plane. That is just some surface on your xy plane like that. And then this lighter green angled one, this is your tangent plane. We can think about it as. My pen has more problems in this class than any other class, I promise. It's frustrating. So that's our tangent plane. This is the xy plane. And what we are interested in is, like it says here, and you can't really see it, those pictures, similar, colors are very similar, but we have this side of that plane, we have this plane here, and that's what theta is. Theta is the angle between these two planes. Okay. So how do we find the angle between two planes where planes don't really have vectors? All we have right now is a way to find angle between two vectors. And so we use a little bit of geometry here. I'm not going to draw this picture too much more. Hopefully you guys can see it. We know that the way we describe a plane is with a point and a vector, right? We know that vector has to be perpendicular to that plane. So if you look at the two vectors that are drawn here, vector k is the perpendicular vector for the xy plane. And then this vector n is the perpendicular vector to this tangent plane. And if you think about properties of geometry, if these two vectors are perpendicular to their respective planes, the angle between them is going to be the same thing as the angle between the planes here. And so we're not really finding the angle between the planes. We're kind of taking a, I don't want to call it a shortcut, but we're going to go back and look at the plane's normal vectors and find the angle between that. So again, this angle here, theta, is the one that we're actually going to find, but it's going to be equal to this angle down here is what we actually care about. I'm not going to try to prove that with geometry, but hopefully it makes sense if you think about this. We're basically taking this original image with this theta and just rotating it 90 degrees to make it perpendicular. The angle is still going to be the same thing. Okay. So that's really what we're going to go through now. If we want to find the angle of inclination between the xy plane and our tangent plane, we're going to go back and say, okay, well, let's use a vector perpendicular to the xy plane, and let's use a vector perpendicular to the tangent plane, which we have some easy ways to go back and represent here. So what are these things over here representing? Well, n in this case, like we said, is perpendicular to the tangent plane. And what vector do we know is perpendicular to the tangent plane? Think about what we just did in the last problem. So which vector have we been working with that's perpendicular to the tangent plane?
The gradient vector.
And so that's what we're going to use for this. We need this vector k, has to be perpendicular to the xy plane. There are an infinite amount of vectors that would do this, but what's a really simple vector that's perpendicular to the xy plane? Let's think, I'll give you a hint. Think about it in component form. What's a really simple component form or vector that is perpendicular to the xy plane?
0, 0, 1.
We think that's the identity vector. 0, 0, 1 is probably the simplest normal vector we can have to display there. So let's use that. Let's keep it simple. If you don't like that, do something else, but keeping it simple helps here. So we know the gradient. If we know the function, we can go back and find the gradient. We know that this now k vector is something very simple. We can go back and work with that. So let's plug these into this equation for the cosine and simplify this down here. So now we have that the cosine of theta is equal to, and again, the absolute values are there just to ensure that we're working from that 0 to pi over 2. It is a little different than we had before, but the idea is still the same here. We're going to have the absolute value of the gradient of f, and we'll just write it that way for now, capital F still, dotted with this k vector, so 0, 0, 1, all over the magnitude of the gradient, and then times the magnitude of that 0, 0, 1 vector. In the numerator, if you think about your gradient, let's actually go back and add it up here to keep this more organized. Remember, the gradient, when we're talking about this capital F that we're working with here, the way we know it's tangent to the plane, is going to be the partial respect to x of the function, partial respect to y, and partial respect to z. That same thing we're just working with. So if you imagine taking the cross product of this gradient and that k vector, what are you actually going to get? What's that numerator going to simplify down to? Yeah, so, or sorry, dot product, do the simple one. Take the dot product of the gradient vector and this simple vector we picked for k, what's that going to reduce down to?
Here's the gradient vector.
Or fz, I'm sorry.
Just fc. It's going to be the gradient vector dotted with this, so 0 times partial respect to x is gone, 0 times partial respect to y is gone. We're just going to have left the partial derivative with respect to z. Okay, so the rest of it we really don't care about here. How about in the denominator? What can we do to simplify that?
That will be
No.
times the magnitude of z.
Yeah, so all this has to have a magnitude of 1 because we're forcing it to be this nice, easy unit vector. So we really just need to know the magnitude of the gradient.
Which again is not going to be, oh no.
Yeah, we don't know that. That could be something else. That won't always be a unit. And so there's just, again, kind of shortcuts, taking things we know, trying to make them a little simpler. That's going to be how we can go back and find theta. So the actual theta, if you want to go back and write it in terms of theta itself, we're going to have the arc cosine of the absolute value of the partial respect to z divided by the magnitude of the gradient. And that you just
For that for all problems, or are we gonna have to? Is that the steps you go through?
we're just going to use this problem. We're always only, anytime it talks about angle of inclination, let's write that here too. Anytime we talk about angle of inclination, we're always going to be talking about between the xy plane and the tangent plane. So it's always just this formula. We're not going to go through and do it for anything else there. But at the same time, if you don't just know this formula, write it down, as long as you understand how to find an angle between two vectors, and as long as you understand that we're not just looking at those normal vectors for the planes themselves, you could theoretically come to this formula yourself. So here we go. We've got this nice little ellipsoid we're working with here. Hopefully that formula looks familiar to things we worked with back in chapter 11. I can remember what chapters they are. We want to find the angle of inclination of a tangent plane to the surface below at the point 221, which I did try to show here, but it is kind of hard to see it. There's this little light pink dot in the middle there, and that's the point that we're working on. So if you imagine that you kind of just lay a sheet on top of this, we're just trying to barely touch this plane, this surface just at one point there, and what we want to know is what angle does that plane make with that positive xy plane. So really all we need to know is the partial derivative with respect to z, and we need to know the magnitude of the gradient. So what is the partial respect to z of this function?
2/3z.
And if we do the whole entire gradient, which we'll repeat that, so 2 out front, that would be 1/6 x. Let's do x over 6. Same thing for y. And then we've already got z. We've got two options here. We can do one thing that's a little more general, but takes more work, and one thing that's a bit easier, but only works in this problem here. We really just care about the magnitude of the gradient vector at that specific point. So you can go back before you substitute anything in and find the magnitude of this gradient, but we really just care about at that point. So let's just plug in the numbers now and see what that gradient vector looks like and just find the magnitude of that. We'll just make the algebra part a little simpler. So we have 2 over 6 or 1/3, 2 over 6 or 1/3, and then 2/3. Okay. I'm going to go ahead and find the magnitude of that before I go back and plug into my cosine. So 1/3 squared is going to be 1/9 plus 1/9 plus 4/9. Or square root of 6/9. Which we've got options. 6/9 is 2/3.
Miss Nicole.
Yeah.
Yeah, 4/9. You wrote 4/6.
Whoops. So weird things I think are pretty cool. How your brain can switch words and switch sounds around,
Yeah.
like in a sentence. It's like the same thing just in terms of math. Like I knew a 6 was going to come next, and my brain just stepped
Yeah,
ahead.
back at home we say the brain is always faster than the fingers.
Yeah.
What you think up there, it's like you can't coordinate as fast as you write. That is why.
And I have problems when I get excited about that too. My head's thinking, and I just talk horrible,
Yeah.
like too quick and hard to understand. And that's a problem I know I have.
Yeah.
Same idea. It is pretty crazy. Bodies are pretty impressive. All right, so we've got our partial respect to z. We've got our magnitude of the gradient. So let's go back and actually find this angle then. So the cosine of theta.
6/9 reduced to 2/3.
Yes, right, because 3 into each of them.
Oh, right.
Okay.
I thought you were doing square root.
I would thought about it. We did the square root of 6 over 3, but the 2/3 and 2/3 up there will work out nicely too. Yeah. All right, so magnitude, so we need this guy. We need the partial derivative with respect to z evaluated at this point. So it's going to be 2/3 times 1 over that magnitude we just found over the square root of 2/3. And if we reduce that, that will just give us square root of 2/3. Whether you're doing a calculator or doing some math by hand, get that. We really care about theta. Square root of 2/3 doesn't matter with a unit circle, so we're going to have to approximate this. So the exact answer for theta is going to be the arc cosine of square root of 2/3, which is approximately, my calculator, And that is in radians, so about 0.62 radians. And then whatever that would be in degrees, I don't know.
Miss Nicole?
Uh-huh.
Could you go over how the square root of 6/9 reduces to 2/3? I just had a different answer on my calculator.
That's okay. Russell asked about that too. Just think about the fraction 6/9.
Yeah.
That fraction reduces to?
Yeah, right.
Yeah, so I just left the square root there. Because I was thinking the other way we can go back and do is the square root of 6/3.
Yeah, that's what I got.
And that's not wrong either. If you want to look that way, that's fine also. But just since I anticipated I knew we were going to have the 2/3, so it cancels down nice, I did that. But yeah, square root of 6/3 would be okay also.
Okay.
Okay. So angles between two vectors. This is one of those things where it's not something we're going to use all the time. It's going to have nice little applications in some places there, which just know it exists, but it's not going to be something that we do heavily, that we do often there. Gradients we'll find all over the place, and tangent planes are useful. But there we go. All right, last example in this section. Find the point on the surface at which the tangent plane is horizontal. We haven't graphed things to start off in a while, so let's graph this guy to start off with. Take these off. All right, so our surface is z equals 3 minus x squared minus y squared plus 6y. Let's orient this a little better. Out a little. Okay, oh, so not a lot. All right, so there we go. We got a nice little parabola. And kind of point them upside down, which hopefully makes sense of being compatible with the x and the y have negative quadratic terms, so we can kind of see this here. And we want to know the point at which the surface has a horizontal tangent plane. So just think about this. Where is this going to, this you have to describe the shape. Where is this shape going to have a horizontal tangent plane?
At its maximum.
At its maximum. So it's kind of leading into what we're going to see in the next section here. We're really asking for where this surface has a maximum point there. It's kind of like the idea of having a horizontal tangent line. We know when the horizontal tangent line in Calc 1 meant the first root had to equal 0, that's when we found our max, and the same thing's going to happen in just a minute here. So there's a picture of what we're looking at. You can kind of see it's going to happen there. If you wanted to go further and kind of estimate it from a graph, that's fine. But let's go back to this and finish the math. So point at which the tangent plane is horizontal. If we think about this in terms of the things we know so far, before we get to the kind of derivatives equaling 0 part that we're going to see in just a minute here, to have a horizontal tangent plane, or just any plane being horizontal, okay, it means what do we have to know about its normal vector? What
It has to be 0, 0, 1.
It has to be 0, 0 something. Let's be a little more general here. 0, 0, 1 would be okay. If we force it to be 0, 0, 1, that'd be fine. But 0, 0, and then something. Any z value would work for this as long as it's going straight up and down. We're good. We know how to find tangent planes, so let's go back and find the gradient of this function, which is going to be our normal vector that we need here, and let's force it to fit in this requirement. So let's get our capital F function here too. And this would be one of those cases where if you didn't want to get the capital F, just know that your partial with respect to z is -1, and that would be a-okay. But if we don't like that little alternate formula, it's really not too much work to just subtract z from both sides. Make that look more clear. All right, so here we go. So our gradient of this function, with respect to x, we have negative x squared. With respect, oh, not negative x squared, just negative 2. Thank you. With respect to y, negative 2y plus 6. And with respect to z, we're at -1. And again, in order for this thing to be horizontal, we want to force this to meet that vector like Edwin said. So we want to make sure that this fits into this over here. Okay. Let's go ahead and start solving. We know that the x component's -2x has to equal 0. And we know the y component, -2y plus 6, has to equal 0 also. Okay. We don't really care about the z. I'll come back to that in a minute. Let's just focus on solving x and y for it now. So x is 0, and y has to be 3 to make that true. The reason we don't really care about the z component, we can go back and solve this for z. It doesn't hurt to do that. But this isn't actually the point on the surface. all this part here, z equals -1, is telling you like the gradient. What's the gradient point that thing there? But it's not necessarily on the surface. We need to go back and say, okay, well, x and y, what are they equal? And then go back and force that on the surface to equal that. So this isn't really wrong. It's just it's not what we're looking for. We want to know where's this point on the surface. That's where the point is like on the gradient, which isn't guaranteed. So anyway, we have to have a normal vector being this. Means x has to equal 0 and y has to equal 0. So if we go back to the original function to find out what z actually equals, 3 minus 0 squared minus 3 squared plus 6 times 3 gives us what? 3 minus 9 minus plus 18, 12. And that is it. That would be our point. So at the point 0, 3, 12, that way we know we're on the surface there, not the -1. That's when we are going to have a horizontal tangent line. Yeah, the math really isn't the difficult part in most of these problems. It's just understanding how we're going to get what we need from the stuff that we're given here. So recognizing the relationship between tangent planes and normal lines and all that stuff there. You can go back and add this to our graph so we can verify. 0, 3, 12. It's right there. Need to do now a little more to actually see the top. There you go. Okay. It didn't ask for the equation of tangent plane, but you can go back and find the equation of tangent plane. Excuse me. Since it's going to be 0, 0 up there, it's a fairly easy equation to come back with. Just x is equals 12. That's all we can have there. So there's the actual equation for the tangent plane. The only thing in this section that's left in the notes there, it says you can do this stuff in higher dimensions. We're not going to go back and do any of it because it's hard to go through and graph it, but same ideas carry through. If we just keep adding in variables to this, all the same ideas keep carrying through there. The gradient's still going to be the normal vector. We're still going to go back and set it equal to 0 to find out the function or where that has normal line. It's just a little weirder to think about normal lines and tangent planes when we're in a higher dimension. We're not going to make examples of that. Okay? All right. Questions? This example does lead really well into the next section. The next thing we're going to do, and really all we're going to spend the rest of the time with chapter 13 is just how to go through now maximize these. Hopefully we've got a pretty good understanding of these three-dimensional surfaces. Hopefully we've got a reasonable graph of what the gradient is doing for us in different cases there. And we're going to say, well, now let's try to find maximum. I mean, really that's when this starts to become applied and become useful. Tangent planes may be useful too, but we want to know where is this thing maxing out? Where is this thing minning out? What values do I have to go back and plug in to satisfy these requirements? So in 13.8, we just talk about Extrema in general. 13.9 is all those word problems. And then 13.10 is a method called Lagrange multipliers. And it's still going through and finding Extrema, but it's under conditions. So like if you have a job and you can only spend so much money on supplies, but you still want to maximize your profit, we can go through and use these methods to kind of find maximums in those cases. But these last three sections are all very similar. They're all related to the same type of thing there, which hopefully is good. It means we're not having a whole bunch of new ideas in the last part of this chapter. So we'll get this started. Definitely not going to finish this, but we've got plenty of time to get through stuff. Absolute extrema and relative extrema. Other words we can call these: absolute are like global extrema, and relative are like local extrema. Are they the same thing? Is an absolute minimum the same thing as a relative minimum? Are those just synonyms, or they mean different things?
Absolutely different.
Yeah, they're a little different. Yeah, absolute's the whole thing. So if you've got some open intervals, some whole entire thing there, absolute is the highest value or the lowest value kind of back to min. Whereas relative or local is just first one closed interval. So with a portion of this, what's the min, what's the max? And we're going to see some theorems here in just a minute. Like usual, think back to good old two-dimensional stuff, just in Calc 1, we're working with this. We use the first derivative for what in Calc 1? What's it tell us?
The slope.
Yeah, it tells us slope. We know that when the slope equals 0, that's where we go back and find a max or min. Okay, we have
pretty much what we just did on number 5, right?
Yep, it is very, very similar to that example there. Okay. In two-dimensional cases, what does the second derivative tell us?
The speed.
The speed, or sometimes we'll say the concavity, or no, not really the speed. That still goes up here. What's the speed with this guy? That's still speed.
Second is acceleration.
Yeah, acceleration.
Acceleration, yeah.
Or concavity, we figure out which what the concavity is. And we also had ways of going through with the second derivative to decide if we had mins and maxes. Remember, we had the second derivative test we can go back and use. If the second derivative at a point was positive, we knew the surface was concave up. We knew we had a minimum. If the second derivative was negative, the surface was concave down, and we had a maximum. So we can go back and use this to figure out that information too. Okay. So we know that. That's going to show up again, something similar there. In 3D cases, we're not going to talk about the same exact parallels here, but what we know about 3D cases is partial derivatives. What do partial derivatives tell us? So let's be specific. What's the partial with respect to x tell us about a function or about a surface?
It is the
Yeah, so this is still a rate of change or a slope, but only in the x direction.
Mm-hmm.
And then similar partial with respect to y, also a rate of change, but only in the y direction. And then that last section, we then talk about directional derivatives, which are similar to partial derivatives, but how do directional derivatives differ? Their rate of change in, yeah, in some other direction. So it's not necessarily the x or the y, but just any direction. So as long as we have some vector, we can go through and describe that. So the directional derivative, noted by this is still a rate of change, but in a given direction. T-O-N. And that's that vector u, that vector u tells us. Which, remember, magnitude of u had equal 1. I always forget that when I'm doing the problem, so the more I remind myself, hopefully the more you guys remember too. So we have a lot of pieces here. There's a lot of overlap between the information it's telling us. We're working with a lot of rates of change. If we remember that example, like Russell said, that example is very similar to what we did in Calc 1, but for a 3-variable case there. And that's pretty much all we're going to do in this section until we talk about another special test for this. Okay, so we have surfaces. Here's an example of a fairly complex surface. I just stole a picture from the book here. Does this have, let's say, absolute? From the looks of this graph, do we have an absolute max?
Yes.
Yeah, kind of in the middle there, it looks like we have an absolute max. Do we have other maximums, relative maximums?
Yes.
Sure, we've got tons of them throughout here. And if we can see the bottom better, we probably have the same situation happening at the bottom. We probably have an absolute min and tons of relative minimums here. So we don't always have just one value, much like in Calc 1, there's lots of options here. If you remember, we were talking about directional derivatives. We had ways of being able to point in the path of the steepest ascent. And we said that that kind of points us to the max, but not always the absolute. It can go to the local. And that hopefully makes sense here. If you're sitting on the surface somewhere over here at this point, and you figure out what way you can travel up the surface the quickest, well, it's probably going to take you to this maximum over here. It's not going to send you down a hill and then back up a hill to get this maximum there. So keep that in mind. That directional derivative stuff we talked about still applies here, but it's talking about going to local maximum. We're going to process a different way. We're not quite going to do that.
So when you do, anytime you do direction, it's always going to take you to the max?
Basically, yes. Let me go back to where we talked about that. I don't remember where it was. I don't know where it was. I know we talked about it somewhere. We had this theorem. There it is, right there. Bottom page 30. So bottom page 30 says the direction of the maximum increase is given by the gradient, okay, which is really says directional through there. But yes, it basically always points to your local max, the nearest. I don't know if saying nearest is the best word for it. It points to, nearest is an okay word. Their situation is not going to be the best word. Yes, it points to the nearest local max. If you had some weird, crazy surface where there's like a really fast drop and then a super quick increase after that, it's possible that max is closer. But since you had a drop first to get there, it's not going to point you in that direction. Like your other max might be somewhere way over here. But since you don't have to drop to get there, it's going to point you to that one. So nearest really isn't the best word. But yeah, it points you to local maximums.
Convenient.
To convenient. To ones where you never have to go down to get to the max. Just as if you keep going uphill, what's the next max you're going to hit?
So in that case, is there, for your directional derivative, can you go minimum?
Yes, you hit a negative. So you say If you say, okay, from this point, if I only ever go downhill, what's the closest minimum I can get to than just taking the opposite of the gradient, which points you in that direction. Opposite as in like make it negative. Just change the sign.
Okay.
Just change the sign. All right, page 41. There's a little picture. So simple surface. We have this guy here. Think about this two ways. If we imagine that this is just taking a snapshot of something on a larger open interval. Okay, because we know that these surfaces go on forever. So this is a paraboloid, keeps going on forever and ever and ever in both directions there. In terms of maximum, what does this guy have? Or in terms of extrema, let's be more general. Does this on an open interval have a max?
Yeah.
Looks like it's right there at the origin. Okay, so we've got an absolute max, probably at the origin. Pen, work please. If I knew a way to always fix it, it would be just frustrating too. It's inconsistent. Absolute max, probably at the origin. Okay, without doing much harder work here, I don't want to say definitely. On an open interval, do you think this has an absolute min? If it's this paraboloid? Yeah, no, it just keeps going down, 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 so no minimum. Okay, but on a closed interval, and let's just keep it convenient, let's keep it on this one we actually see here. Who cares what the actual numbers are? But in this little square interval that we see, from x is some number to some number, y is some number to some number. On the closed interval, do we have any maximums?
Yes.
Yeah, so we can call it the absolute in this case, or if we call it the relative, that would also be okay. And again, it's still at 0, 0. How about minimums? On the closed interval, have minimums?
4.
Yeah, it's got these 4 little points here. We don't know exactly what they are, but yeah, it has 4 relative minimums.
They would be absolutes.
For the interval, they would be.
I'm just saying that.
No, yeah, that's a good question.
I'm
I'm going to try 4. And 4 absolute mins on the interval. We'll just do that. Okay, so for the whole surface, they're not really absolute, but yeah, on this interval, they are definitely absolute. Okay. I know most people don't remember Rolle's theorem, but if you happen to remember Rolle's theorem from Calc 1, this is basically the same thing that's saying there. Rolle's theorem in Calc 1 says when you have a closed interval, you will always have a minimum and you'll always have a maximum. And that's what this first thing says right here, the extreme value theorem. So this is very similar to Rolle's theorem from Calc 1. Like I said, I don't know how many of you remember that stuff or want to remember that, but there's a lot of parallels, so I'll try to point them out. Okay, so basically this says you've got some continuous function, which that continuity piece is always going to show up. We're going to work with a lot of continuous functions here on some closed and bounded region, and that's what makes this theorem special. Okay, we're only talking about working on closed regions. If we force this continuous surface to be on a closed region, we're making sure it starts and it stops. Basically, what's happening there. We're saying, okay, no asymptotes. We're not going off forever to infinity, which wouldn't have a max. We are forcing this thing to start and stop. If we go back and do that, we will have at least one minimum value and at least one maximum value. Okay, we're going to have at least one of each of those. So the picture above, we have that max, and we've got 4 minimums. It's okay to have 4 of them. We have 4 of them there. So what that says. The next two are more definitions and actual theorems here. So the relative extrema is probably what you would guess saying there. So this is the fancy way of saying if some points are relative minimum, then all points on the surface in this interval are going to be larger than it in terms of the output. If it's a relative maximum, all the points on this surface are going to be less than it relative to the point there. Okay. But this last one for critical point is probably also what you would guess if you think back to critical points from Calc 1. But this has got a little bit more to it that's going to be useful for us in these examples, which we'll probably get to tomorrow there. So critical point are going to be occurring at 2 places, where the gradient of the function equals 0, or where the partial derivatives do not exist. Remember critical points in Calc 1?
Yeah, vaguely.
How do we find critical points in Calc 1?
Double derivative. And then it was like a chain between.
I think you're making it more complicated. Maybe you're on the right track though. The simple way of finding the critical points is where the first derivative equals 0, and then where the first derivative is undefined. This says basically the same thing, only we have partial derivatives instead of just first derivative. But we're doing essentially the same exact thing there. We know the gradient is just the partial derivatives, So we're saying like that last example, we'll render these partials equal 0. We want to make sure we have this horizontal tangent plane. We have no change in the x direction or the y direction, force them to be 0. But if they're undefined, we also have to go back into those cases too, because that's not going to show if we go back and find those partial derivatives. Okay. Yes, yes, you are. So it sounds like. So the relative extrema theorem is probably what you'd expect. Again, this stuff follows greatly from Calc 1 there. If a function has a relative extrema at a point, so if we have a critical value, or if we have, sorry, I said it the wrong way. If the point is a relative extrema, then that point must be a critical point there. Not all critical points are extrema, but all extrema are critical points, if that makes sense there. So we're going to do the same thing we did before. We're going to go back and find our critical points, and then we're going to go back and check to see if they're mins and maxes. Sometimes checking for mins or maxes is more difficult for dimensions, and that's what we'll worry about more tomorrow. So we'll pause there. We'll finish this up tomorrow. Might not be able to get much more of the homework done with the 13.8 stuff there, but feel free to take a look if you have questions. Let me know. Okay, that's that. See you guys on.
Yeah.
All right. Thank you. Have a good day.
Yep, and I will upload this. If you happen to talk to people that were gone, I'll put it on Canvas.